Okay, so now I'm going to start talking about unit vectors. This is definitely new from what we did last year. Okay, unit vectors basically make use of the components of vectors that we learned about in the last section. Okay, a unit vector it's a vector with a magnitude of 1. You're like, well, why is that useful? Well, it's very useful. Okay? We set up these unit vectors along the x, y, and z axes. Being able to do that allows us to take the components of the vectors and make it into, break it off so that we can see the components and we can add vectors together very easily. So let's take a look. Okay? Usually what we do, we separate these unit vectors into the one vector in the x direction, one in the y, and one in the z. So now, if I set up axes like this, x, y, z. Okay? When you go to college, a lot of times your professors will make this the x, this the y-axis, and this the z-axis. Not only doing that, we know that x and y, we're used to x and y being along these axes, so we can put z along here. It's still a right-handed coordinate system. We'll learn about what that means in just a bit when we do cross product. But the basic idea of a unit vector, okay, is that we're going to have one unit vector that goes along the x direction. Okay, we're going to call that the I unit vector. Okay, and we designate unit vectors with a little vector hat, a little caret. Okay, instead of doing this, like we do for most vectors, we put a little caret on top of it instead. This we call the y direction. We use j hat. And along the z direction, we use k hat. Okay, so we're going to use I, j, and k as our directions. So now, let's take a look at how this would work. So let's just say I have vector A. We're going to keep it all positive for simplicity's sake. This will equal, say, 3i plus 4j plus 2k. Okay? So let's just say we have a vector like this. It has an x component of 3, a y component of 4, and a z component of 2. Okay? So what we've done, we've broken down this vector into its x component, its y component, and its z component. And it would go like that. Okay? So now, if I were to draw that on this axis here, pause it if you need to redraw the axis. Okay, I'm going 3 in the x direction, so it'd be 1, 2, 3. I'd start off here. It'd be 4 in the y direction. 1, 2, 3, 4. When you take multivariable calculus in college, you'll have to do a lot of these, and they are not fun. The hardest part of multivariable is trying to draw the vectors. Okay, so now this would look something like this. Okay, so that would match up there, and then it goes up 4 units. Okay, measuring it out, get a little bit higher. So our unit vector would look something like this. Not our unit vector, our actual vector here. Okay, so this is coming out like that. So now this, we kind of draw these parts in so we can see how they react to each axis. We can see the y-axis there. We can see the x-axis along here with that line. We can see the z-axis coming off that line like that. Okay? So that's how we would draw these three-dimensional vectors. Now, here's the thing. The reason why we put these together like this, adding vectors in unit vector notation is incredibly easy. So let's just say that I had another vector that was, and I'm going to put a negative one in this one, negative in this, negative 5i plus 3j minus 6k. Okay? Well now, our rules for adding vectors, okay? Remember last year, I set it off into an east-west axis, a north-south axis, and we'd add them together. That's all this is, okay? Really what we were doing then was unit vectors, but we weren't setting them up as actual unit vectors. We were breaking it down by components. So now, A plus B, I'll give you the general form of this, is going to be AX plus BX I hat plus AY plus BY J hat plus AZ plus BZ K hat. Now that's a big long equation. It's really easy, trust me. A plus B. I add 3 to negative 5. I get negative 2i hat. I add 4 to 3 plus 7 j hat. I add 2 to negative 6, negative 4 k hat. And I'm done. That's how I add these vectors together. Now, this is significantly easier than doing it by component, than when you have magnitude angle formation for your vectors. Okay? We're going to take a look at that situation too, and it's much harder. Let's take a look. So let's just say that I have two vectors. I'm going to say A is equal to 40 at 65 degrees north of east. Okay. Now let's just say I have vector B that is 25 at 40 degrees. We'll go north of west. Okay, and this is, we're only going to do 2 dimensions here because 3 dimensions gets incredibly complicated. But now, if I want to add these 2 vectors together, okay, remember back, okay, I'd have you guys draw a picture of what this would look like. All right, and when we set up our axis, we go 40 at 65 degrees north of east. We just kind of sketch it out a little bit. And then 25 at 40 degrees north of west, which would look something like this. This might cross the line, might not. Okay, this was 65 degrees. We're going to set up another axis here. This would be at 40 degrees. Okay, so now we had to break this down into components, which is really all we're doing here with unit vectors. So now I'd have my east-west, my north-south. Okay, it's really my I hat. This would be my j hat. And I have vector 1, vector 2, and total. Okay, so now I set it up like this. Okay, 40. Okay, my x component, which is east-west, 40 cosine 65 degrees. Okay, that's the x component. It's positive. North is going to be positive again, 40 sine 65 degrees. Okay, we're good there. 25 at 40 degrees north of west. Now I just say negative because I'm going west. 25 cos 40 degrees. Here I'd say positive 25 sine 40 degrees. And it's positive because it's going north. Remember, the north-south doesn't affect the east-west. So now, plug this into a calculator and say, all right, 40 cos 65, get 16.9. 40 sine 65, 36 point, put 90, I go 36.25, and then I go negative 25 cos 40, negative 19.15. Let me just check the mode that I'm in. Okay, I'm in degree mode, that's good. Okay, 25 sine 40, and 16.07. Okay, then I have to add the components together. This is really where I'm just adding AX and BX. Okay, I add these together, and I get, let's see, that's basically 17. So 2.25 is going to be negative, so I am west. I add these two together, which is pretty easy. That's 52.32. Okay. So now I want to figure out what my x and what a is. A is equal to a. I shouldn't call it a. Total is going to equal total x squared plus total y squared. Okay. So I do that. 2.25 squared plus 52.32 squared, square root, answer 52, so t is equal to, I'll just write it out, this is t squared by the way, negative 2.25 squared. The negative doesn't matter because it goes away with the squared. 52.32 squared. So when I do all that, I wind up with 52.37. Okay. Then I still have to get theta. Theta is going to equal inverse tangent of ty over tx. So I get inverse tangent of 52.32. I don't worry about the negative, I just know that it's west, so I just say 2.25. I don't worry about the negative there. I know that it's going west, so I just say theta is equal to second tangent 52.32 divided by 2.25. And this is 87.5 degrees. And this is going to be north of west. Okay, so this is much harder than doing unit vectors. Okay, unit vectors makes things easier. Whenever you have an opportunity to answer in unit vector notation, by all means use unit vector notation. You'll be suckered sometimes into using magnitude angle. Really, you could have stopped. Okay. They give you magnitude angle. You don't necessarily, on the AP test, you don't have to answer in magnitude angle formation unless they say so. If they don't say anything, you could have answered t is equal to negative 2.25 I hat plus 52.32 j hat and be done with it. Or being more specific about it, you could have called it west and north. Okay, saying west, you can take away the negative. But use unit vector notation whenever you can.